lambda m is somewhat less, because this product has to be a constant. If T increases, lambda m will decrease. So you have looked into a couple of things: Stephen's law, Wein's displacement law, Kirchhoff's law of radiation. So now let's do some questions. The first question coming up: there are two bodies A and B. Their emissivities are 0.01 and 0.81 respectively. They have the same area and same radiant power. The temperature of A is 5802 Kelvin. Let lambda be the maximum, let lambda be the wavelength corresponding to wavelength of maximum spectral radiancy. It's given that the difference of lambda A and lambda B is 1 micrometer. Can you find what is lambda B and what is TB? This is the question. This box basically means I can put A or B, anything here. If you put an A, it means wavelength of maximum spectral radiancy of A or that of B. So let's see this question. See, let's take up this idea. They have the same radiant power. Radiant and emissive power one and the same. So we can say epsilon sigma AT power 4 for both of them, meaning for A and for B, is same. Now I did not put AB because they have the same area, it's given there. So this area gets cancelled. Sigma is also same, gets cancelled. So what you basically get is 0.01 5802 power 4 equals 0.81 TB power 4. Can you calculate TB from here? How much are we getting?
1934 Kelvin.
That's right. 1934 Kelvin. Also, because of Wein's displacement law, lambda ATA will be equal to lambda B TB. So what does this mean? This is one equation, and this tells you that lambda B is bigger than lambda A. Here it's given that the difference is 1 micrometer. It's not given which is bigger, but now we know that this is bigger. Lambda B minus lambda A is 1 micrometer. So from 1 and 2, can you solve and find out what is lambda B? So those are the answers you are seeking. Yes, so lambda B happens to be how much?
1.5 micrometer.
1.5 micrometer. Is that okay? The next idea. See, if you have a body, let us say of temperature T0, and it is kept in an enclosure which is thermally insulated of temperature T0, will this body lose temperature or gain temperature or remain same? It should remain the same, the surrounding is same. So what we say is, what's happening is, this body emits radiation to the surrounding like that. The emission of radiation is epsilon sigma AT power 4, and it will also get some radiation from the surrounding enclosure. Surrounding enclosure is giving everywhere, but also it will give back. So I am showing by red and black. Red arrows are going out, black arrows are coming in. So what it gets back, I don't know, but the result is 0, because you said that its temperature doesn't change. So what it must be giving must be getting back. So we know that X happens to be equal to epsilon sigma A T0 power 4. This is supposedly T0, right? So what it absorbs is epsilon sigma A T0 power 4. Now let us say the temperature in the second experiment, this is T and this is T0. T is greater than T0. Now what will happen? What the surrounding is giving is the same thing, because the surrounding has not changed. The enclosure will give the same thing, enclosure remains the same, but this is going to emit a little more. I'll put more number of red lines. So what is emitting is epsilon sigma A T power 4, whereas what it is getting back is this. This we say is the net emissive power. So the net emissive power equals epsilon sigma A T power 4 minus T naught power 4. This is a more practical way of writing the Stephen's law. Because when we say Stephen's law, it assumes as if the body is isolated. There is nobody around it. But in every practical situation, when you have a body with temperature T, the surrounding will have some temperature T naught. And if the body gives it to the surroundings will also give it to the body. So you will have this as the net emissive power. So this is the one, the more practical way in Stephen's law is used. This idea which I shared with you is called as Prevost theory of heat exchange. So now we will Prevost, Prevost theory of heat exchange. Okay, so this is the effective idea we're talking about. The next idea we're talking about is Newton's law of cooling. Suppose you have a body having temperature T and this is the surrounding temperature such that the temperature is surrounding plus delta T and delta T is much less than surrounding temperature. I'm talking about this kind of an idea. Say it's like a coffee cup. Coffee we are having at 60 degrees centigrade, a hot cup of coffee, and the surrounding room temperature let it be 30. So what is the difference of temperature? Difference delta T is 30 degrees centigrade. And surrounding temperature is surrounding is 30 degrees centigrade. So that will be in terms of Kelvin 303 Kelvin. So surrounding is 303 Kelvin and delta T is 30 Kelvin. So it is only 10%. We're talking about that. So if that be the kind of difference of temperature which will happen in practical cases, so how do we do it? So this body, its emissive power is effectively speaking epsilon sigma A T power 4 minus, I'm writing Ts power 4. This is the surrounding temperature. And you know that from calorimetry, the quantity of heat transferred to a body is so much. If I differentiate, I get dq by dt equals ms dt by dt. If I'm talking about loss of heat, then I put negative. So I will say minus ms dt by dt equal to this. This is the starting point of Newton's law. So let us rearrange this. I write this as minus ms. T I can write as, see, dt is also equal to dt minus ts, because whether you take the differential of t minus ts dt minus t of ts is constant. So this is 0. So we can write this as t minus ts also. Epsilon sigma A ts plus delta t power 4 minus ts power 4. This difference of temperature I write as delta T, capital delta T, equal to epsilon, negative sign I keep here, epsilon sigma A by ms. Let's simplify this. If I simplify this, I get Ts power 4 outside, 1 plus delta T by Ts power 4 minus Ts power 4. I'll use binomial approximation here. 1 plus x power n is 1 plus nx. If you solve this now, what do you get? Minus d delta t by dt equals Ts power 4 and minus Ts power 4 gone. You have 4 Ts cube. So we will write it as epsilon sigma A 4 Ts cube by ms delta T. Can I write like that? This is the equation of Newton's law of cooling. the rate of cooling is proportional to the difference of temperature. If a hot cup of coffee is there 60, surrounding is 30, then 60 to 50, let us say it goes in 5 minutes, then from 50 to 40 it will take more than 5 minutes. Because when the temperature is higher, the cooling is faster. That's the idea of this. There's a differential equation you have got, which we can also rewrite it like this. I integrate it. At 0 time you have the initial difference of temperature. At final time you have the final difference of temperature. The answer comes out as log of delta T final by delta T original equals minus KT, or in integral form delta T final equals delta T original e power minus KT. Either of them is called Newton's law of cooling. Yeah, are you okay with this? Any problem with that? We'll be applying it in a small question. Let's see. Yeah, are you fine with this? Can I rub it off? I'm going to rub off everything except the 2 boxes. Are you clear on the derivation? Every step? Yeah, fine?
So can you explain all of it again?
Yeah, which one? What are you saying? This is the MSL power. You have temperature, surrounding temperature for this body having a mass m and specific heat. This is the MSL power, okay? And from calorimetry you know that if a body is given a heat, quantity of heat Q, the MST minus T naught is the MS delta T is calorimetric Q equals MS delta T. I differentiate this, you get this. If I put a negative sign here, it's negative sign because there is loss of heat. We are assuming that this energy is going as heat. Although this refers to electromagnetic energy, but ordinary temperatures, most bodies lose it as heat. Heat means infrared radiation. What we are ordinarily calling heat is infrared radiation. So, thereafter we are using this T equals Ts plus delta T. We are writing it like that. Power 4. This dt, d of T minus Ts is dt minus dTs. But dTs is 0 because temperature of a surrounding doesn't change. A hot cup of coffee will not make the room hot. So surrounding temperature will remain the same. So we are writing it in this form. This is delta T and this is power 4. Take out Ts power 4 common. 1 plus delta T by Ts. 1 plus x power n is 1 plus nx. When you put that, you will be able to get Ts power 4 minus Ts power 4 cancel. 4 Ts cubed comes out. Delta T comes out. This is minus, this is K. That's a K which is a local K. There is no name for it. Its value will differ but depending on situation because it contains the mass, specific heat, area, room temperature, etc. So we get this and we integrate it to get this. We are going to employ it in solving a question. Is that okay? So let's see. Say I have a cup of coffee. The surrounding temperature is 30 degrees centigrade and this T1 is 60 degrees centigrade. It cools down to T2 50 degrees centigrade in 5 minutes. My question is, in how much more time will it cool down to 40 degrees centigrade? Let's say this is the question. So I'm going to use this formula. This formula I can rewrite as log delta T naught by delta T final equals KT. This negative sign I remove and make it a reciprocal. This means log of delta T naught means original difference of temperature 60 minus 30. What is the final difference of temperature? 50 minus 30. How much time it takes? 5 minutes. This is your equation 1. Equation 2, you take this as 50 as initial and 40 as final. Initial is 50 minus 30. Final is 40 minus 30 equals how much time it takes. Well, that's what I want to find out. T. So how do I solve this? Just do 2 divided by 1. So this will become T by 5 T by 5 equals, this is 30 by 20, 3 by 2. And this is 20 by 10. You will get log 2 by log 1.5. So T equals 5 times log 2 by log 1.5. Now you would require a scientific calculator for this. I've got this answer, so I'm just writing it. But you can't find it out without that. So this is about 8.55 minutes. So that's how we use this formula in the logarithmic form. We have used this formula of Newton's law of cooling to get our answer. Now I'm going to use another form of this law. We will see how to derive that. So let us say this is method 1 and I'm going to do now a method 2. See, I'm going to derive this first. The formula. See, ordinarily, if I say what is speed, you will say distance by time. What do you mean is this? But actual definition is this. Here, what is missing is limit delta t tending to 0 is missing. If you have this here, then both are equal. Otherwise, they are only approximately equal. But many times when this gap is small, a small time, we equate it to infinitesimal time. This is an infinitesimal time. So just like we say this is average distance by average time, this is instantaneous speed, but we say more or less they are equal. If you do it like this is called differential approximation. So I'm writing this also the same way, minus delta t by delta t equals k delta t. I'm making that approximation here. Can I write like that? What does delta t mean? See, this is minus of, what is the final difference of temperature? T2 minus Ts. What is the initial difference of temperature? T1 minus Ts. This is the difference of temperature. How much time it takes? T is equal to K. What is this delta T? The difference of temperature. But there is nothing called difference of temperature. You have the initial difference of temperature and the final difference of temperature. So let's call this the average difference of temperature. Initial difference of temperature plus final difference of temperature by 2 should become average difference of temperature. So if you solve this now, what do you get? You get T1 minus T2 by T equals the minus sign, TS cancels, and this is K times T1 plus T2 by 2 minus Ts. This is the form we'll use. This is the linear form of Newton's law of cooling. This doesn't require a scientific calculator. Both these would require. So let's see how to use this last box that we have derived just now. So I rub the rest of it. I'm rubbing this part. So I use this formula in the first part. T1 minus T2.